we have to start. So, recording is going on, right? Okay, so let me welcome again from here to the week 1 of TS session. So we'll start with recalling what has happened in the classroom, and then we'll solve some of the problems. Because if this is first week, we have easy problems, I should say, so we can solve them easily. So I have written something from the classroom notes so that we can recall what has happened. Right. So we had started with definition of field, right? What are fields? And then from here we assume that we know some of fields like q and real numbers, and these are q means rational numbers, and we define complex number field, right? As a vector space over real numbers, one way, and this was defined like Rx modulo x square plus 1. Okay? And this was proved that it is field and it contains R and solution of this polynomial. Solution of polynomial x square plus 1. And this is the smallest field, which is defined like C, which contains real numbers and the solution of x square plus 1. And from here, next step was to define topology on C and then identify this C with R2 plane. So the standard topology on the plane, what we have learned is same here when we give C metric is the structure. Okay, so metric is given by norm, and norm was given like this. Norm of Z is basically defined like Z into Z bar, and this belongs to real number, positive real number basically. So this way we give a structure of metric space on C, and that it matches with standard metric structure on R2. So from here, next step was we define conjugates, right? Conjugates of numbers. Why we say conjugate? Z bar, which was defined like if x minus iy, if z is equal to x plus I. We say that these two are conjugate of each other because for a real polynomial with real coefficient, when z is a root, z bar is also a root. That is why we say these two are conjugate of each other. They happen to be roots of same polynomial. Okay, same polynomial with real coefficient. This way, right? Next, what we did, we have defined a topology. I mean metric structure. So from here we define a topology on this by first defining balls. What are balls? Basically, these are. Let me define. Let definition. Let Z not belonging to C and R be a positive number. We say there is this D Z not R, which is ball of radius R around Z in the complex plane for Z not some point here, R radius here. We say these are numbers Z inside C such that Z and Z naught, these two are close. Okay? Their distance is less than R. So the point Z which are close to Z naught. that way. So this is also called disk. Okay, so in the later course it will occur many times. So after this we defined open set. I think if you need I can mention them, but open set and close set, etc. Should I define or should I leave this? I think this is open sets are basically, let's say, a subset of C. We say it is open if for every set inside A, then you should focus on topic. बिल्कुल सही. Uh, we'll focus on problems because we have 2 hours. We'll quickly finish this in 5 or 10 minutes. Okay, so let's finish it. For every z belonging to A, there exists R positive such that D, Z, R, this around Z is also contained in A. So this way. And closed sets are basically complements of open sets. Then we talked about limit points. That is, I think, clear. Interior and closure of sets that I don't want to discuss. And quickly, we see what is convergence of sequence. Zn sequence convergence. Zn be a sequence in C. We say Zn converges to Z if Zn minus Z modulus of this. Now it becomes real number sequence. This this is also a sequence, and this is sequence of real numbers. And if it is converging to 0, then we say that Zn converges to Z. So this way convergence was defined, and that limit commutes with addition, multiplication, and conjugation. Okay. So for example, limit n tends to infinity, Zn plus Wn, this is equal to limit Zn plus limit W. So this way some properties of this. And now connectedness and compactness, these two are things. Okay, so why I am mentioning all this? Because when we will solve the problems, some of the problems will be statements of the theorem. So that is why I would like to mention some of the theorems. Okay. uh, right. So connectedness and then compactness in 10 minutes we'll quickly cover this, and problems are not that difficult, so we'll solve them 1 hour later. Connectedness. So to define connectedness, first we see what is disconnectedness. So we say two sets are okay, this way. Let A be subset of C. We say is separated, is disconnected or separated if A can be written as union of two disjoint open sets. This notion, okay, this notation is for disjoint, where U and C are open. Same definition. Similarly, we can define separated, where we are taking U and V closed set. Okay, open in or close in a, that can be changed. Right. So one example was given about real numbers. What are connected subsets of real numbers? So a subset of X, sorry, a subset, let's say X of real numbers is connected if and only if it is an interval. it is an interval. So, so one problem is here. Can someone explain why this is so? If it is an interval, how we saw it is connected? One direction is clear. When it is connected, it is interval. Connected implies interval. This is, I think, easy. Using contradiction method, we can show if any point in the middle is missing, that will disconnect the thing, right? So it should be interval. Now other side is little difficult, but I think you can do it. Okay. If you don't understand why interval is connected, using this definition, of course, this is the definition we want to do. Okay. Right. So there are some more things when we have continuous maps. Let's say start f from x to y. X and y are topological spaces, and f to x is continuous map. Okay. I think many of you know what is continuous map, right? Inverse image of open set is open. That definition we are using. So how many of you know? Can you raise your hand so that I can know you know definition of continuity? The definition I want to tell that yes, sir. Okay. So I know. Okay. So when f is continuous and x is connected, good. When x is connected, then fx image this is also connected, right? This is one theorem which was proved in the classroom. So I'm just mentioning this. I will not prove this. Okay. If you want to know the proof, go through the class videos once again. Right. So there was one more thing about complex planes. Open set is connected if and only if it is path connected, right? An open set is connected if and only if it is connected to a path, right? So I don't want to mention that. Okay, leave it. Now coming to compactness, some of the results we will recall. Compact. Right. What is compactness definition? Basic. Okay. Connectedness. It is for separated. It is separated. This is definition for separated, and with those subsets which are not separated, they are connected. Compactness means for any let A be subset of C, we say every open cover has finite subset. बिल्कुल सही. Right. So we say A is compact if every open cover of A has finite subgroup. Right. This is the definition, and then we had some exercise left in the class. So I think we'll solve that exercise also. So there were some example of finite sets, empty sets, and sequences with the limit point added to it, they becomes compact. So if you have an infinite sequence like 1 by n, and if you don't add 0 to it, then it is not compact. Okay. So this way we had some examples, and then we had a theorem. this theorem. So compact subset in a metric space, they are closed. In a metric space, compact sets are closed. And then we had three notion of compactness: compact metric space, uh, equivalence, which was limit point compactness. Of course, I'm not going to prove this, but we'll see what these are. Sequentially compact, and those which are simply complex, sequentially compact metric spaces, metric, they are compact metric space. Okay, this equivalence. Limit point compactness was basically for every infinite set, there is a limit point of it inside. Okay, sequentially compact means for every sequence we have subsequence inside it. Okay, so this equivalence, after this we are going to solve. So in the class, okay, in the assignment problems, first 4 5 problems are very easy, right? Those who know this much data, or they can solve what is conjugate of a plus ib, something like this. So those problems I'm not adding here. So I'm adding some which are interesting problems, like problem number 6. Okay, so the assignment which is given to you, from the next time I will not solve them. Okay, similar question I will solve so that you can try your own. But this week I have no new problem, so that we can discuss on that. So we'll solve 3 4 problems in your class assignment. Okay, so problem number 6. Okay, so in the problem number 6 we are given two metrics d and d1. We say these two metrics are equivalent if every open set with respect to d is open with respect to d1, and vice versa. Okay, so here we are given balls, notation for balls with respect to d1 with respect to d. Now so starting with a metric space xd, we are creating a new metric space xd xd1, where d1 is given by this formula. So any of you have solved this problem or no? So there are three questions here. So okay, if you have not seen how to do this question, we'll quickly see how to do. Let's see first part. Every disk D inside X open with respect to XD. Of course, it is open. This disk is open up. Okay, is also open with respect to metric D1. So how to show something is open? So here this is main question. Okay, so this is open and not necessarily vice versa. That we'll see later. So first we create a ball. Every point is an interior point. बिल्कुल सही. So let me draw the picture and then we'll see. Okay, let's say this is a ball in, this is our D, and now this this whole thing is D. And we, if we want to show open with respect to D1, what we have to show, pick any point Z, there should exist a ball with respect to D1 inside it, right? We want this blue ball which should completely lie inside. This is, let's say, dz, which should completely lie inside capital D. Okay, so how to prove this, how to get this small ball dz, this small blue ball, right? So this is our idea to start. Okay, so we have enough space here, right? We are given, let d is equal to, d is defined as d, the center is z naught, and this radius is r. So this is already we have took. Now pick any point z inside this. Let z belongs to d. What we have to get, some epsilon, we want to get some epsilon positive, such that d z epsilon, this should belong, this should be contained in capital. Okay, so every time I'm using capital D. So is there any confusion, or this ball should be denoted by d delta? Now it is clear. Okay, so we want to get an epsilon. How to get this epsilon? That is the problem to solve. Okay, so I will construct a line from z naught to z. Okay, and I will extend to the till the circumference, and we'll get some point here in the circumference. Let's say it is a. Then we'll consider this if this length is delta. Okay, so I am considering this r minus. Okay, I'm just written here. I have just written delta defined this way. Delta is nothing but z minus z naught, this distance, minus, or r minus. R is the biggest radius of capital D, and we are subtracting this distance. Okay, so whatever left is, that is delta. Okay, so we should get, if we have delta ball around z, so we, from what, from here we get, if we have d z delta, this is contained in d delta. Is this clear? And if we get something, some epsilon which is less than delta, that ball will, this is the biggest ball, I will say. This is the biggest ball around z which is contained inside d delta. So, but we want to get lesser than that, so no need to worry about that. So consider this ball. Let's say we get some epsilon. We'll calculate what is epsilon. is there epsilon exist or not. So okay, so d1 z epsilon, okay, d1 z w, here w is variable, w belonging to c, okay, such that d1 distance between z and w is less than epsilon. This is d d1 z epsilon, right? So the problem is on existence of epsilon such that this contained inside d delta, right? So calculate this, solve this, and get the answer. So this is nothing but dZw upon 1 plus dZw. Okay, and we need less than epsilon, and so my internet connection was good. Okay, so we are solving this 6th number question where we have given a metric space X and a new metric which is defined as a T1, and what is the question which we want to answer is the first part of this part, open with respect to T1 or not. The first metric, sorry, first ball with respect to D, is this ball open with respect to metric D1. So that is what, how to prove this. First we consider a ball with respect to D, first metric, and in this ball, to show it is open, we pick any point Z here, and we should get a D1 ball around it. D1 ball which should completely lie inside the bigger ball. Okay, understood? I think you understood till now. So we get a ball with respect to D, and we want to show it is open with respect to D1. That is all we are doing. So how I started? We consider this ball. I'm noting by D delta because D and D delta were confusing. Now I pick a point inside D delta. Now we want to get D1 ball around Z of some epsilon. This is what we want to calculate. Epsilon. Some epsilon ball should be contained in D delta. The problem is computing what is epsilon. So this is just for observation that uh, if delta is r minus this length, z and z naught is center, okay, then this ball is contained inside d delta, and this is the biggest ball contained inside d delta. This is something like, oh, okay, more bigger, sorry. Right, we want to calculate epsilon, so we will solve for epsilon. So this is less than epsilon. I'm solving for this. Okay. Now this is dZw less than epsilon 1 plus dZw. From here, what we get, dZw minus epsilon dZw is less than epsilon. So from here, what we get, dZw 1 minus epsilon common, dZw is common, and epsilon here, right? From here onward, this is dZw less than epsilon upon 1 minus epsilon. I think till now it is fine. So all the steps here are if and only if. Okay, so this is next line. these steps are required. Now what we get from here, when we have this ball less than epsilon, d1 ball, d1 epsilon ball around Z, it is related like so. We want dzw to be contained inside this ball, biggest ball, should be the distance should be less than this delta. This this part should be less than delta. So we'll bound it by delta. So delta is this length. Delta is the biggest dzw which is contained inside the ball, d delta. From here we'll calculate what is epsilon. Epsilon is okay. How to calculate from here? Epsilon, okay. Epsilon is what we want to calculate and delta is known. Okay, so don't be confused here. Delta is this length. So let me change the color, white color. This is delta. Okay, anyway, come here to see this part. So epsilon is less than delta 1 minus epsilon. From here, what we get? Delta epsilon. Epsilon plus delta epsilon is less than delta, and from here we get epsilon less than delta upon 1 plus delta. So this epsilon will work now. Okay, so each steps are if and only if, so we can go back anywhere anytime. So when we have this condition, we can choose such epsilon. We will have this condition. From here we will have this, and from this we will get this inequality, and this thing shows when dZw is less than delta, this is containing this point W is containing this force. W is containing it. So this collection hold W, which are epsilon close to Z. They are basically delta close with respect to D. Those which are epsilon close with respect to D1, they are delta close to D. So that is how we saw W is equal to D. So the same thing. Okay, I will not explain. If you have problem in this explanation, you can ask. So then this is false because similarly from D1 we can get a formula for D, and that will give vice versa. So, we showed that this ball is open with respect to D1, and from this equation I'm saying just as D1 is defined in terms of D, D can be defined in terms of D1. So this is vice versa condition holds. So the balls here are open in the other space. We are changing the topology, but they are equivalent, I'm saying. So first two options are incorrect, and this is third option correct. But D is not known. What D? But okay, so right. If it is a, if it is a rectangle, no, then U delta will not work. So this is in a general metric space, and the picture here works. Okay, if you take point near the corner, no balls. This is general picture. Okay, why I'm considering it as a general picture? Because This works well with the calculation. Oh, is there any mistake here? No, no. So all I'm using here is triangle inequality kind of. Okay. So rectangle type of balls, there also I think it should work. Let's say we go with the calculation once again, and then we'll see if there is any problem. So we consider d delta a ball with respect to d. Now we consider a point z inside this. Okay. Now what we want is d1 ball around z, which should be contained inside d delta. So why I'm writing this delta? Right. So if you so if you see this column, this row, delta is defined in such a way that delta is less than r, and this is the maximum length. All the if you use triangle inequality, so everything will be less than r. So this delta works here. This step you should understand. I think. So how don't go what is ball right now, rectangle type of ball, but this I think you need to understand this, and this will show what is element here. If w belongs in this small ball, delta ball, what happens? D z w, this is less than delta. And what is dz z naught? This is less than, or this is exactly equal to, let me write, this is equal to r minus, oh, I should not use mod here, because this is a general metric space. We are understanding it as a complex numbers. That is what the problem. So I should mention here d d z z. I understood the problem. Now it is d z z naught. Right. Now calculate the distance between d z naught and w. If it is less than r, then w belongs to d. This is what we want to check, and this is it. Okay, right? Break into two steps and use this hypothesis. How delta is defined. Understand it as a hypothesis and put it in the triangle inequality. You will get, for example, d z naught w. This is less than or equal to d z naught z plus d z w. But how delta is defined? Put it here. Z naught to z r minus delta. This is less than or equal to r minus delta plus dzw. And zw, dzw, we have further hypothesis is less than delta. So everything is less than r. This is less than delta. This minus delta plus delta get cancelled and less than r. So we go. Okay, so there was some issues which had been addressed because delta was defined in terms of modulus. This would be in terms of d. It is it for general metric space. Okay, after this star, understanding this star, what we want to show is written here. This is our claim, and we want to understand what is written inside epsilon, what epsilon ball. So we get this lesser epsilon, and still we don't know epsilon. We want to calculate, but we are going we are know if we know that epsilon exists, we calculate epsilon. So we have calculated this way, and finally we see that this is a positive number. This is a positive number, and condition is that epsilon is less than this number. And of course, it exists now because between 0 and this number, real number, there is there is large number of real numbers. So there are very uncountably many real numbers. So we can choose some epsilon. So this kind of epsilon exists, and all the conditions work. Okay. So D1 ball around Z has been contained inside this bigger ball. So this way we have shown D delta is open, and the converse is vice versa part is also true, because what happens actually when you have D1, it is defined in terms of D, and from here if you know D1, you can define how D. So D gets similar expression, very similar expression, just like this, and you get a solution of that. So these two topologies are equivalent. Can we go to the next question? Go through these lines once more. We'll share the PDF. So from the last step is go. Such epsilon is means D1 Z epsilon. This is contained in D. Can we go to the next question? Yes. You can unmute yourself and ask. You can ask by unmuting yourself.
So in this question, we have basically established epsilon is lesser than delta by 1 plus delta. It
Yes.
it seems like the RHS of D1 of x comma y. So if there are other such problems like this, then we have to find whether epsilon is equivalent to RHS of whatever new metric that has been defined, sir. Is my question clear?
No. So I will explain again the same thing. So question is not clear to me. What you want to ask? RHS means what? Uh, Santosh, which RHS you are talking about?
RHS of d1 of x comma y, d1, let d1 of x comma y be defined as d of x comma y by 1 plus d of x comma y. Define another
Hmm.
metric on the metric space x comma d. So
Hmm.
basically, we have established that epsilon is lesser than delta by 1 plus
Yes.
delta, and delta is another metric. So if there are similar types
Delta is
of
not a metric. Delta is a real number. This defined this way. This this is also R is also real number, and dz z not. This is also real number.
okay, sir, I get it now.
So if you draw the picture, it will be very clear. So basically, what I did is first took dz naught r, we pick a point here z, and what we saw, we concluded after all this calculation, dz, I mean there exists epsilon positive such that dz d1z epsilon, this is contained in dz. And similarly we can show if you have d1zr, there will exist dz epsilon which will contain in d1z not r, right? So this is vice versa kind of condition. So go through these lines once more. If you don't understand, you can ask. Okay, let's see next question. Okay, so question number 7 is about sequence of complex numbers. So we are overall 6-7 people. I would like to ask if one is correct or not. I will ask some explanation. If you know, you can answer it. Otherwise, I will explain, of course. Anyone want to wish? So you have opportunity to talk to me. Zn is Zn is a sequence of complex numbers, and a subsequence is converging to Z naught. And we are saying that we are extra saying that Zn is bounded also. Then Zn is convergent to Z naught. Is this true or not? You can reply by comments also. Okay, I think that because you are lazy, let me say that this is not true by taking Zn is equal to minus 1 to the power n and take the sequence Z2n subsequence. This is convergent to Z naught is equal to 1, but it is not convergent. But limit Zn does not exist. So this is someone answered B, C, D, B, C, D. So how is okay? Let me write these three are true and saying this is false. How it is false? This is for A. This is for E. Why? Last one is false. We should give in such a cases. We should give a counter example of this proving something. Series of complex numbers which converges and which is not absolutely convergent. So here again, I think this will work minus 1 to the power n divided by n. This is, sorry, 3 n. This is sequence of real numbers, but real numbers are also complex numbers, right? So the same idea will work here. So these two are false. How B is true? B is these two are false. B is true. Someone is saying it is true. How it is true? A subsequence converging to Z naught and Zn is Cauchy sequence. Then Zn and Zn converge Z naught. How will you write this? Because Zn is Cauchy, what happens? So let me explain. Just explain. No need to write the solution. Because Zn is Cauchy, what happens? After some stage, distance between Zn it becomes so small that it tends to zero. When n tends to infinity, distance between terms of the sequences, they are getting closer and closer. Okay, very close, epsilon close. If someone comes and gives me epsilon, there will be some stage will get epsilon close to that, and one of the subsequence converges to some number. What happens? The actual sequence, which is of course after some terms, all the terms are very close because of Cauchy criteria. Okay? So the subsequence where subsequence is converging, this Cauchy sequence will converge there. Okay, this is the explanation. If you want to write it, you can write it. The part okay. However, see, Zn is a bounded sequence. Zn is converging to Z not if and only each of its convergence subsequence has limit Z. Yeah, this is correct. I think okay. Should I explain this? The idea is same because Zn goes to Z, Zn minus Z. This this is very less than epsilon for every n after some n naught, right? So even if you take subsequence, any subsequence, there will be terms after n naught. They all will become epsilon close to Z. Okay, so they will have same limit Z. Okay, so this is how we understand this solution, right? So I'm not writing very well. It is like I'm understanding, and that that's all. We need boundedness. Of course, if you take this sequence 1, 1 by 2, why we take bounded? Wait, hmm, I think we don't need to take boundedness. You know why we don't need? Because if you assume one side, Zn goes to Z, this means it is convergent, and convergent sequences are bounded. If you go to other sides of equivalence, each convergent subsequence has limit Z0. Oh, each convergent subsequence has limit Z0. If it was written that every subsequence has limit Z0, then it would have been fine. That is where we need bounded. Okay. So one side is clear. When it is convergent, it is bounded, of course. But other side, it is not clear. It says that convergent convergent subsequence has limit Z0. If it was talking about all the subsequences, not only convergent, then it would have been fine. Okay, right. So it is better to take bounded sequences because otherwise, if you remove the boundedness criteria in the main hypothesis, you just make it all subsequences goes to Z. All subsequences converges to Z. When Zn goes to Z0, then all the subsequence also goes to Z. All subsequence all subsequence of a convergent sequence need not be convergent. They will be convergent. Okay. Will you explain how, Sandeep? If Zn goes to Z0, what happens after some stage, after some n naught? Zn and Z naught, they're very close, epsilon close. So what subsequence is coming from sequence only. So the terms of the subsequence, their terms also inside the actual sequence. So leaving a finitely many points till n naught maybe, everything is epsilon close. In case of unbounded sequence, so you should have said all subsequences of sequence need not be convergent. You are already taking a convergent sequence and you are talking about subsequence. So if you take convergent sequence already, all the subsequences, they will also be convergent. So actually convergent sequences are Cauchy sequences here. Cauchy sequences are bounded sequences. Converging means infinity. Okay. So I don't know from which book you are talking about. Convergent for me actually means it converging to some point. Okay. So those which are going to infinity, basically I would say they are divergent sequence. Right. So there is some problem with our notations. Can you produce an example? Example of what? Where if you do not use object. Uh, if I may. So in case of unbounded conversion, in case of unbounded, of course it is incorrect. Right. So I will say this: one, one by one, two, one by two, three, one by three. I'm considering a sequence A. Okay. Four, one by four. A convergent subsequence, only convergent subsequences, subsequences of 1 by n, which is lying inside here. Okay. They are of this form. They are subsequences of 1 by n. This is some A to n. And all those subsequences who are converging, they become subsequence of this. But limit zn exists and it is equal to z naught. This is unclear. Limit an does not exist. Just because the sequence is unbounded. Okay. This is sequence, this is never exact. And 1 by only convergence sub all the convergence subsequence have limit 0. Convergent subsequence have same limit 0. This hypothesis is true, but we are talking about here. Convergent subsequence have limit 0, all each of it, right? But limit does not exist. This is the example. That is where we need bounded. Okay, this is what we need bounded in C. Okay, let's go to D. Zn is convergent, so is mod Zn. So who will like to answer this? Zn is convergent. to, let's say, z naught, then mod zn, this is also converges to some number L positive. Someone would like to explain, then you can explain otherwise. We'll do this. This is very simple. You break it into, right, Sandeep, you're doing good. Xn plus I yn, you break like this, and what z naught is, let's say, x plus iy, then xn is going to x and yn is going to y. And how is mod zn? This is basically xn square plus yn square. This was defined this way, if you remember. Maybe there was some square root, but that we don't care. If an is square sequence convergence, then under root an is also convergent. For example, no example, forget that. So this converges to x square plus y square. If there was a root, this will converge to that. Okay. Right. So let's see next question. I think you understood this very well. We are almost 1 hour. We'll finish in 20 minutes maybe. If you have other doubts, you can. So question number 8. We have two metric spaces and continuous function between them, and we have to see which of the following are correct. The set fu is open in Y whenever U is open. This is not the definition of continuity, and we don't know about image, right? Do you think what is definition of continuity? F inverse of U is open in X whenever U is open in Y. This is continuity definition of continuity. Okay, and we don't know about images, so first option is incorrect. Second option, do we know? Second option is about F inverse of compact sets is compact. Is this so? Is this the case? Of course not. I will say not, and we'll do some counter example. If you want to give counter example, you can comment or you can directly tell to. So there are many continuous functions which are basically very basic. First examples of constant functions is kind of. If f was continuous function, constant functions basically. So f inverse of any set, y complex set. Okay, very important. My fault. What we have to say in the case complex for all. Right. Take y to be point and it fails. Function is constant and it is continuous as well. Okay. And singleton is compact also. So only compact set inside y is y singleton. and the inverse image will be full X. And take some non-compact thing, let's say real number to real number constant function. Okay, y is singleton. In that way, the only compact set inside y is singleton. Should I write, or you understood? P is false. Why? Reason is this: if f from R to singleton 0, or basically whatever singleton thing, same matrix, just same topology. Singleton has only single topology. So in this case, this is y, this is x, only compact set empty singleton, and three mazes are not compact. And this makes the text constant. This is what, when y singleton, it is constant, right? Not the text constant function from R to R or of R. Right, it fills up. So both these options are incorrect. We have understood. So when f was a constant function, this also discards A and B. Open sets are not more open sets inside image, because image becomes singleton. Let's see part C. Fk is compact for all compact sets inside X. So this is good exercise. Here we should spend time, because everything else is just giving counter example solve. So this is option C. And K is inside X, compact. Then f of k, this is also. How will we go proving something like this? We'll take an open cover of fk, right? Because fk is covered by that open cover. Let me go to prove this. Let fk is covered by union of u alpha, alpha belonging to some indexing set, and this is u alpha, alpha belonging to some indexing set. This is cover of f, open cover of f. Now from here we should get finite subcover, right? This, okay, when we write that, we don't write bracket. So we should know this. There is some mistake. So you should also learn this. Since K is compact, yeah, we have to use that. How we need finite support from here. What we are going to do, F inverse of Q alpha. We consider this. And because Fk is contained inside this bigger union, F inverse Q alpha, when you take union over alpha, K will be 6. And from here you get, because these are also open. Why? because f is continuous. Right. And now K compact implies there exists I, or there exists some 1 2 in indexing set up to n, such that u1 f inverse of ui, when you take union of this I from 1 to n, K is contained. But this will imply that K is contained in union of ui, I from 1 to n. This ui belongs to this cover, because 1 to n, these numbers are from index from here on. So they are some alpha, finitely many alpha, which covers fk. So we get the proof, right? If you have problems, you can ask. Otherwise, we'll go to next step. We had some open cover of fk. We created some open cover of k, taking pre-images of those open sets which were used in that cover. Now, because k is compact, we get some finite subcover of this, and same finite subcover is again pushed out, applying f, and said that fk is contained in u. We get a finite subcover, and it shows that fk is also compact. Okay, so I think no one has doubt, so we can go to next. X is complete, so is y. X d1 is complete, so is y d2. This is wrong. Why? This is wrong. Why? Use some counter example. Take some continuous function where one is complete and another is not complete. Do you think real number is complete, right? There is completeness axiom, which says that any subset of real number, which is, let's say, bounded above, then it has supremum. If it is bounded below, it has infimum, right? Any Cauchy sequence, it has a limit, right? So this says that real number is complete. But open intervals, are they complete? Let's say open interval 0 1. Is this complete? Is open 0 1 complete? Let me say again what is definition of completeness. Every Cauchy sequence should have limit points. Right. Santosh and Sandeep is just saying it is not. For example, 1 by n sequence will work. Right. Is Cauchy but not con. Now you get some continuous function and so that y is incomplete. Why? We don't know about anything y about y. For example, you take this continuous functions, constant functions, and take some, let's say x is equal to real number, y is equal to 0 1, and define function, constant function from r to, or from x to y. F of x is equal to 1 by 2. And we don't know y is how big, is y complete or not. Constant functions don't say anything about y. They will focus only on one point, where the image is going, right? So we don't know if y is complete or not. So this is false. They are saying y is complete I'm saying it is not always. It is not always. Sometimes it is. For example, here if it was domain y was real number, then it was complete, but not always. So this is false. Now last option. K and L compact subset of metric space, then their union and their intersection. They are also compact subset of X. See, one is using the theorem about intersection. Intersection of closed set is what? K and L. K intersection L is closed, right? Because K, L, these two are closed. Finite intersection of closed set. No, infinite arbitrary intersection of closed set is closed. But anyway, this is closed and K intersection L. This is contained in K also, and these two are compact in a metric space. So though both are, these two are closed, it is also closed. Closed subset of compact is also compact. This is compact. Closed subset of a compact subset are compact. So intersection part is clear. Okay. What about union? I would like to see if someone answer this. Finite union and intersection of compact sets is compact. Right. Finite union, finite intersection, they are always closed. So here it is closed. Compact. Oh, is this proved in the class directly? Or we okay. About union it is true, just because any open cover of the union will be after restricting will be open cover of K, will be open cover of L also. And both K and L are compact, so both gives us finite, maybe 100 open sets for K, 200 open sets for L. We will calculate all these together. 300 open sets will cover K union L. So this way union is also right. Someone wrote it is correct. Finite union of compact sets is compact. So option is correct. These two are logic behind that being correct. Okay. So let's see next question. What is the so this is our last question and we'll finish up this. Let X be non-empty connected metric space. X to real number is a continuous map which takes only integer value. Is F constant map? What is your answer? see, X is connected, and if you have a discrete set, so integer values, which takes integer values. How integer, they're discrete inside real numbers, right? So what are smallest connected set, singleton, no, inside a discrete set? Because every set, every single, yeah. So this is basically connected set is basically single point. So this is correct, right? You are thinking with me. This is very good. Yeah. So let's see next part. We have given circle S1. Is this connected? Is S1 connected? What will be your proof for this? So you are saying that it is correct. You can speak to me by unmuting yourself. How will we say this is connected? Okay, you don't want to say, but let me explain how it is connected. Okay, you are saying it is not connected. So you should give me two disjoint components. Both should be open or both should be closed, and they should be disjoint. Let me wait for one minute so that you can give. I'm waiting. Then we'll explain why it is connected. If open disjoint, then limit point be excluded. Right. So no such cutting edge allowed. Right. 2 point. Defined by a path, they must lie. Right. Right. So this is connected, of course. I will say S1 is connected. I will explain why. So someone said that it is path connected. It is very fine. This is actually a single path, I will say. We have this map 0, 1, 2, S1, X goes to e power 2 pi I X. This is continuous. This is continuous map, and this is a single path. And now you have to say that this interval is connected. 0, 1 is connected. इसको एक बारी प्रूफ कर लेना. तो रियल नंबर्स में intervals are connected. Okay, and they are path connected. So this is connected. So f of or gamma is continuous. 0, 1. This is a theorem. This is also connected. This is equal to S1. So S1. Okay. So when X is connected, we have seen that and F is continuous. This 2 implies Fx is connected. So this was the statement used here. Okay, so S1 is connected. Let me see next part. F from X to Y continuous function. U is connected subset of Y. Then F inverse of U is also connected. Is this true? Yes, tell me. Need not be. Of course, it is not true. So give me some example in this case. X is equal to, let's say, 1, 2, 3, y is equal to single one, f constant function. So, but one is connected, y is connected, f inverse of 1 is x, x is a discrete topology. I'm giving it discrete topology. Okay, so C need not be true. So what about D? X is non-empty connected metric space. Non-empty, and there is some element connected. X2 are continuous. That is not constant. Yeah, there are 2 points in the image. So X is large. X has 2 points. If X has 2 points, it has uncountable points. If they are in different images, their image is different. So let me write whole thing. X non-empty. F from X to R non-constant. Continuous. Non-constant means it has at least two images, and X is connected also. It is given. So image should be connected. From all these things, we conclude that Fx is connected. And inside real number, right? Now, what are connected subset of R? They're basically intervals, right? It could have been singleton, but it is saying that function is non-constant. This is important. Don't forget that. Okay. So Fx is an interval. Is a non-trivial interval. I mean, this is non-singleton type. And intervals are basically uncountable. So this implies X is also uncountable. Something which has image uncountable, that should have already uncountable. Otherwise, that will give us counter virodham uncountable. So D is also correct. Now what about E? This is last question. The set C minus F, where F is finite set, is connected. I'm saying this is correct. Right. Sandeep also says it is correct. So Sandeep would like to explain, or I would explain last one. So C is identified with plane R2. And if you miss some finitely many points, whatever left is path connected. And that path connected, and C minus F, C minus F, F is finite set. C minus F is open. Finite, this will imply F is closed, because finite sets, why finite sets are closed? Closed sets should have all, they are defined like whatever limit points of the set are, they are inside the set. In finite set, there are no limit points, so we don't worry about that. So they are closed, right? No limit points, so they are closed. So F is closed, C minus F is open. right? And there was one theorem about open sets when they are connected by paths, right? C minus F is connected because it is open. We are using if and only every point is connected by path. It is path. Is this true? We want to show it is connected, but we know that it is path connected. So this is how we know that it is path connected. This is this is very nice way to do this. Uh, I think it needs no explanation. If you don't understand, tell. Take any 2 points inside the plane. You can connect by the line because you are missing, let's say, finitely many points. These points are missing somewhere. Pick any 2 points and connect them by line. If there is a point missing between the line, you go through the other way. Go in 2 steps. First go like this and you can connect by sequence of line line segment. That means they are all joined together. One line segment ends, second line segment starts. This way you can connect all the points. Okay. So I hope I have done something meaningful. If you have still some doubt, you can stay and ask to me. I'm available for more 10 minutes. And those who don't want to ask anything, you can leave.
Hello.
Yes.
Yeah, actually, I'm a working professional and I'm trying to like sort of take this course. Uh, if I go like the way you're approaching these problems, right? Like only one way is working. Like I've read real analysis and linear algebra, the prerequisites, but if you suppose you want to go to the solutions or to the solve a problem from first principles, from the definitions itself. So
Right.
how to do that? Like it's very difficult to do it from the right from the basic definitions. For example, definition of this connected set, differentiable or something like that. So and if I look at that standard books like Rudin or whatever, like they don't have any examples at all to guide us as to how to like look at these things. So what would you recommend that I do? Like
There is a book by, this is well known. I don't remember the full name, but S.K. Mappa in real analysis. And S.K. Mappa also writes on, I think, algebra, linear algebra. For
okay.
these things, that reference is very nice. I have done many things from there. And there are many other books, not only this, contemporary, also this thing. Okay, no problem. There are many books which give you proper understanding, but you should have asked early to your professors, maybe that would have been very nice. But of course, uh, there are in complex analysis, I have not found many books which are very understandable from the basic principles that you are telling. But Professor Kumarisan, if know, you know Professor Kumarisan,
No, no,
S. Kumarisan.
I'm just a
You,
working professional. I'm not
okay,
a student. I'm like in late 30s, so I'm just like
okay,
studying this for
okay,
yeah.
okay. So S. Kumarisan has also written books on many like complex analysis, also topology,
Hmm.
and there he explains very well. If you are
Okay.
new to the subject,
Yeah.
you should see these books on Kumris. So first of all, for mathematical understanding, he has written foundation course in mathematics. This book
Okay.
is for understanding mathematics, how we talk what are epsilon delta definition,
Hmm.
and then real analysis and complex analysis. These are very nice books. You should look.
Okay. Real analysis, I was able to understand till differentiability and
Hmm.
that sort of thing, but like, but I couldn't solve all the problems in Rudin because it's really like time consuming and it's impossible, really. Like so,
Exactly.
that is why like I want to like some guidance as to like how to approach. I'm engineer, so how to approach mathematics, that close reasoning. So, yep.
Yeah, your Walter Rudin book says, I know it is hard to solve the problem, but there are easy books. First, you understand the theory part, then it is fine. Sometimes you don't need to solve all the questions. If you have understanding of the theory,
Okay.
someday you will be able to solve.
Okay.
So it takes times. Yeah.
Yeah. Like I'm just like, yeah. Thanks.
Okay. What is your name? Maybe Chandra.
Yeah.
Okay. ठीक है चलो we'll see next week, and if you have doubts you can post on discussion forum. There also I'm able to resolve your issues. Someone had asked already about something, we can reply there. Okay, see you next week. Bye bye.